Hello, we are from RoboSub, and this is our video on sensor optimization. To start off with, I am Chris Nathman. I am a senior in computer science at Washington State University. For RoboSub, I am the computer science team leader. And for the sensors, that just means I write software for them.
And I'm Tom Schmitz. I'm a senior electrical engineering major at WSU. I'm the electrical engineering team leader, and I create the hardware and firmware interfaces for the sensors.
All right, so an overview of the sensors on our sub. To start off with, we have the sonar system, which all that does is find where sound is coming from, specifically the sound from the pinger in the RoboSub competition. Next, we have the cameras, which are used to identify the objects and pictures on competition elements at the RoboSub competition.
Then we have the depth sensor, which pretty much tells us the depth that we're at. Then the IMU, which pretty much tells us which direction we're going and at what rate.
All right, we will now discuss our competition strategy for using these sensors. The first task in the RoboSub competition is the gate, and we are going to discuss gate and path at the same time because they are extremely similar, as path is just a revision task. So as with pretty much every task in the competition, we're going to use the depth and IMU sensors because those are really useful for just sort of basic driving of the sub. Then for the gate and path, there's a lot of important visual elements. So the cameras are going to be used a lot as well. For the gate, we have given it a confidence level of about 90% because in previous years, we've been able to do it fairly consistently. And since the gate is the first task of competition, we will put in a lot of time and effort to ensuring that it's functional.
Then we have the bins. It utilizes the downward facing camera, and it also uses the depth sensor and IMU for basic navigation. We gave lifting tops off bins a 10% confidence level, and that's because we don't have any hardware implemented to do that quite yet. Then we gave dropping a 50% confidence level because we already have hardware implemented for that to drop markers into the bin. And we already have a board designed, but no firmware yet.
All right, next up is the buoys, which just like the other task, it's going to use depth sensor and IMU for navigation. Then the buoys are just, of course, buoys with pictures on them. So we're going to use the cameras to be able to identify those. And seeing as it's another fairly simple vision task, we assume that we'll be fairly decent at doing that if we can do the gate. So we gave it a confidence level of 80%.
Then we have the torpedoes. It uses the cameras and sonar to locate the target. It also uses the depth sensor and IMU for basic navigation purposes. We gave this task a 10% confidence level because we don't have the torpedo launcher implemented yet.
Last task is the Octagon and bottles, which is going to use depth sensor and IMU once again. And then this time it's going to use sonar to navigate to the pinger, which will tell us where the task is. And then it's going to have to use the cameras to identify the tables and bottles so that we can pick up the bottles and put them on the tables. For confidence, we are 80% confident in our ability to surface within the Octagon because we have been able to do that successfully in pool tests. And it's not a particularly complicated task. For moving and placing the bottles, we are only 10% confident because we have not actually created the arm yet, and we have no idea how effective that will actually be. Next, we will talk about the development and testing of our sensors.
So first off, we have the depth sensor. There was a custom board built to read the depth from the depth sensor, and when we initially created the board, we just tested it to see if there was some basic communication by dipping it in a cup of water. Then after that, we just test it during each pool test. Then we also have the IMU. We decided to go with a commercially available IMU. There was a custom table belt to calibrate the unit. And in this upcoming year, we plan to fit it with step motors to finally calibrate the IMU.
All right, for the sonar, it's basically just a system on chip connected to some hydrophones, so we can sample them really quickly, which will give us more smooth waveforms to analyze. And then once we get the waveforms of the sound, we will perform cross correlations between the channels on each axis. So there's 4 hydrophones, one sort of like origin, and then the 3 to cover all 3 axes. We cross correlate between the origin and each axis to find a time delay, and then from there it's just a little bit of trigonometry to figure out what direction the ping actually came from using the time delays. Now for actual testing and development, we have been just putting the hydrophones in a bucket of water in the lab. At least in previous years during the pandemic, that's been a little bit difficult, to say the least. So that just told us, the bucket just sort of told us if the hydrophones were picking up sound and if they were generally getting a good direction on it. And then for more accurate testing, we would just actually put a pinger in the pool and then put the sub in there and see what the hydrophones told us. And then next for the cameras are going to be using a deep learning system. And to assist with that, we have a Coral USB accelerator, which makes tensor operations much faster. So that will help with the processing speed and ensure that we can make better use of the images we get. And during the pandemic, since we were unable to actually go to a pool and place objects in it, we just made some printouts on paper of the expected game elements and then just made our own data set using those pictures so that we can train our cameras using those to see how well it works. But eventually we will create a real data set using objects in the pool, which have more of the features that would really be present at competition. All right, that is our video on sensor optimization. Thank you for watching.